and welcome to RISE Learning Machines seminars. RISE is Sweden's research institute with 3,000 people working on topics spanning from bioeconomy to digital systems. Specifically, the computer science department works on applied AI projects for the benefit of society, and we organize the weekly Learning Machines seminars as part of our Center for Applied AI Research. This meeting will be recorded, and if anyone wants to be removed from this recording, please let us know. Also make sure to check out the collection of great talks on our YouTube channel. Today, I have the pleasure to introduce Tomasz Trzcinski, who is an associate professor and leader of the Computer Vision Lab at Warsaw University of Technology. He is also computer vision group leader at IDS NCBR, which is a publicly funded Polish Center for AI. And he's also affiliated with Tuplox and the Jagiellonian University. Tomasz had his PhD from EPFL in 2014, and he's been a visiting scholar at Stanford and at Nanyang Technological University. He has research interests including efficient machine learning, continual learning, SLAM, visual search, and representation learning. And the topic today will be zero-waste machine learning. And we're very much looking forward to hearing about this. So with that said, I'll hand over the word to you, Tomasz.
Thank you so much for the invitation. It's a great pleasure to talk to you today. And well, I hope I will convince you that zero waste is not only about recycling rubbish and environmental issues related to waste management, but also applies to machine learning. So let me start with the motivation. It is big, well, for some people, it looks like a washing machine. For others, it's more about, I would say, a dishwasher. This is actually a detector that we use at CERN within Alice experiment to register the beams of particles colliding against each other. And it consists of thousands of metal detectors that register the signal, the electromagnetic signal. Now, the size of this is quite big, but it also converts to the amount of data that it collects. Every hour, several petabytes of data are collected by this device. And to actually save it, store it properly, we use machine learning algorithms to detect the quality of this signal. If we are too slow, if we are not efficient enough, we are not able to do so. And we need to basically throw out a lot of data that is being collected. This is the main motivation I had before starting the efficient machine learning project or research topic, but there are several others that may be also familiar to people outside of CERN. High performance computer centers, where we use our machine learning models to train even more complex systems. The GPT-3 model was trained according to the data that I have with over $600,000 budget, and that's only training, not even the neural search, architecture search, or parameter tuning, etc., which is obviously part of what we machine learning engineers do every day before even jumping into the final training. And last but definitely not least, there are applications for which the latency is critical, like autonomous cars. In latency sensitive applications that require machine learning models to run super smooth and super efficiently, a millisecond of delay can cause serious damage. Let's imagine a kid jumping in with the ball on the street, and then inefficient algorithm not detecting it at the right time. So the motivations I guess are clear for efficiency in machine learning. That's why a lot of researchers have focused their work around this topic. Not only myself, most of them so far focused on constraining the optimization in some sense, either through a limited budget of computational resources, or by minimizing the model size, by quantizing it, by reducing its size, by pruning the networks, and so on. Now, my research is coming from a slightly different angle, not constraining the models, but making use of what's available to them. More specifically, and that's why the zero waste machine learning and the title. More specifically, I'm focused on 3 pillars of zero waste machine learning. That's the research path I follow, and I try to promote it out. First is conditional computations. So in principle, what we want to achieve is to dynamically adjust the processing path of a model for a given data sample based on some intrinsic properties of data or based on some analysis of the data sample we have. A second pillar of zero waste machine learning is partial evidence, so methods that leverage evidence or partial information available at runtime, at inference to the systems. Like, let's say you're in the forest and you want to detect the classes of objects around you, the likelihood of, and you have the certainty of being in a forest because of some external sensors, then obviously the likelihood of seeing a skyscraper or New York taxi cab is quite low. So that's where you can leverage partial evidence to speed up or to increase the efficiency of your model. And last but not least, knowledge accumulation. This is related to continual or lifelong learning, where accumulating knowledge within the model is of paramount importance. And if you do not accumulate the knowledge, if you need to train the model from the scratch every single time the data distribution changes, you occur, or additional costs occur. And these costs are not only financial, but also environmental. So that contributes to the zero waste machine learning research paradigm. And let me jump into a single or every single one of those pillars and talk a little bit more about our research in those areas. So conditional computation is the first one. The standard, or one of the standard groups of conditioning computations within neural networks, which is the predominant topic of my talk, as the contemporary machine learning likes them the most, is early exit methods. There are other families like mixture of experts and several other approaches, but early exits are actually, I would say, the best and simplest way of explaining what conditional computation can do and what it's all about. So if you say have a model that processes an image and goes consecutively from block to the other, usually it's convolutional modules that are then ended up with fully connected layers. What early exits do, they propose introducing intermediate classifiers, the ICs, and exiting the information, exiting the decision about the model early on, so before the final one. Now, they typically waste computation because they do not look at the results of the previous ICs when they compute their own. As you see here, the arrows are only connecting the blocks and the ICs, not the ICs in between each other. So when we looked at this from a research perspective, we asked the question, are early classifiers smart enough? So are they smart enough so that they can accumulate some information that the later ICs do not? In a sense, can we, make use and recycle some of the computations they do? And the way that we wanted to verify this or find the answer to that question was through measurements. So we looked at the metric. First, let's suppose that CM is a set of correctly classified samples of the mth classifier. Among all samples incorrectly classified by that IC, we count the fraction that of those samples that for which any previous classifiers answered correctly. So in a sense, we look at the situations where the mth classifier was wrong, while one of the previous ones was right. And we called this metric a hindsight improvability because it, in fact, measures how much better a given IC is, or how much better a given IC can be if it reused the information from previous ICs. We could use it to study how wasteful early exit models are and see how much performance we can still save. And for every IC here, we plotted the results of this hindsight improvability, and it seems that the early ICs are actually quite smart. So the results suggest that the answers from previous ICs do contain some useful information. In particular, for the last IC, we noticed that over 70% of incorrectly classified examples were classified correctly by one of the previous ICs. So that's the metric above 0.7. This means that we could avoid 70% of mistakes if we were able to perfectly reuse past information. And to overcome this problem, or to make use of this observation, we introduced two techniques that reuse computation of the previous ICs. And the result was the zero-time waste method that was presented last year at NeurIPS. And it's based on recycling the predictions. So the first component we propose is based on cascading the connections. The main idea here is to pass the information from the IC directly preceding the current one. We simply concatenate the original input to the last linear layer with the logits from the previous IC. This is a very simple extension, and it adds minimal complexity to the network, but offers significant improvements in terms of performance. The second improvement, or second module of our zero-time waste approach is ensembling. So what we can do is we can ensemble the results of internal classifiers. We can combine those outputs. In particular, we combine them using the weighted geometric mean, because we found out that this approach mitigates the impact of overconfident answers of specific classifiers. So when they're overconfident, this reduces the impact of those. And so we evaluated the performance of this method by checking the accuracy for many possible inference time limits. Inference time here is counted with respect to the base model, and it's counted as average number of floating point operations needed to process the entire test data set. In this case, each result on the plot is a curve, because we can vary the confidence threshold with those early exit methods. It can be set arbitrarily, and the plot shows that zero-time waste outperforms the previous early exit methods because of the reusing, because of the recycling the computations, as well as base network. So base network also performs worse in terms of accuracy, which is the reason. The reason for that is that it combines, our method allows to combine, ensemble the results of the ICs, which in base metal does not apply. So early exit methods are quite well known now. The question is what can be done next? A lot of those works that we see and we notice discuss similar ideas to ours. So reusing ICs, or combining their responses, or maybe making them more complex, or using more complex decision functions. The problem with that is obviously it adds some computational complexity, but we postulate that the unified view on early exit is needed. So we see this through a relation with several other works, like plugin networks that I will describe in a second. They leverage partial information or partial evidence at inference. And the thing is that they input the information to a certain depth of the network that can be thought of as an extension of our early exit methods, where we don't only exit the information, but we can also input that. Residual adapters, these were proposed in 2017 by Vidaldi and his co-authors. It was used for multitask learning. Now here we can think about our add-ons within the network as residual adapters, and maybe look at them from this perspective of efficiency as well. And then mixture of experts. This is the second family of conditional computation methods that is of relevance, and they allow to route the information or indicate a specific processing path of a given sample based on routing procedure. And in this case, we could combine the mixture of experts model with early exits to even further increase the efficiency of our methods. The second group or second pillar of zero-waste machine learning research that I'm focused on is related to partial evidence. So that's the situation where we are able to get some more additional data either from sensors or some coarse level granular information from ground truth. So let me explain maybe an example of this kind of method. For instance, if we have a scene classification problem, we want to have an input image and process it through a Bayes network, predict the label. For instance, if it's a park or indoor space or a river, etc. Now, the question we ask with partial evidence is, what if there is some additional information available at inference time? Like, for instance, that some classes are certain, or they come from a certain course level granular information. Like, you see the photo here, and you know that it's going to be either outdoor, natural, or man-made. Because of additional sensors you have, because of GPS, because of the location of the photo, etc. Like, how can we incorporate this partial evidence into already trained model? So if you have the model already trained, frozen in the weights, and you want to incorporate this information, how do we go about that? So this is the paper we published 2 years ago at WACV. The idea was to use plugin networks, so-called modules that are plugged in within the neural architecture, and then they incorporate partial evidence as an additional vector process through fully connected layers, and without the need for retraining of the base model from scratch. It should allow also fast inference phase so that it's still efficient. And we look at the modules that we can implement as part of our plugins, and we allowed the computation or the attachment for the layer activations to be either additive, affine, multiplicative, and residual. In fact, the additive one was the one with the highest accuracy, so that was the one we picked from the ablation study. And at inference, when we looked at the information, or we look at the performance of our network, once again, you input an image, you process it through a network, and then you get a final label. Is it a river? It doesn't look like a river to me, so it's incorrect. Now, if you plug in this additional information from the partial evidence, you're able to find the correct label, which is the park in this case. Now, for the training, we do not change the base model weights. So those model weights stay unchanged, but what we only update is the plugin network weights. So to propagating the loss, we compute the difference between ground truth and only update the plugin network's weight within this within those models. What is interesting, what we found interesting actually, is that for plugin networks, the representations that they learn do include information about this partial evidence. Although, even though the loss function that we use to optimize that does not include the partial evidence as part of the loss. So here we plot the representation learned by base model on the left and the plugin network on the right. And the output of the layer where plugin network is attached is projected to 2 dimensions using t-SNE as well as for base model. And this single point is one example from SUN 397 dataset. And as you see, the partial evidence labels, so those coarse-grained labels about outdoor, indoor, man-made, natural, etc., are well separated in this t-SNE space, while in the space of representations visualized with t-SNE, rather than the base model, which is quite overlapping in between those classes. So the conclusion is that because of this, we are able to easier separate the classes, and that ends up with better results in terms of accuracy. So we were able to overperform or outperform SOTA, state-of-the-art on 3 different applications: scene categorization, image annotation, and semantic segmentation. However, what was a bit disappointing, I would say, is that we achieved this at some additional negligible but still overhead in terms of inference. Now, our idea was to increase the efficiency of those models, and that's why we're looking right now at actually speeding up the processing of plugin networks with some routing procedures, and looking at increasing this efficiency by, for instance, routing this the specific samples through specific parts of the network without even this tiny additional inference time. So that's where we are heading right now. The other project we are looking at with this partial evidence is inspired by the work of Tina Dutillars from KU11, where they look at visual exploration with 360 degrees cameras. And the point there is that you have a camera 360 degrees, and you try to reconstruct the entire 360 view with several glimpses. So not looking at the entire image, but with a minimal number of looks or just analysis of certain patches. And with that, we hope to, well, it's also a partial evidence setting. It's just a conditioning based on how many glimpses you have, but you have some information about the entire scene, and you want to reconstruct the other parts.
Thomas,
yes.
Do you want to take questions during the talk, or do you want us to
whatever works for you guys? If you're using the time of the talk for this, I'm happy to answer them straight away. That's okay.
So during the training of this, do you feed this extra information for all the training data points, or do you also train with data points without this extra information?
No, it's all they are all coming with the additional partial evidence. We probably may think about some of this weakly supervised setups where you only have for some of them the information and for some of them not, but in this case, for the evaluation and so on, we used partial evidence for all.
Mm-hmm. There's also a question in the chat, but that's related to the early exits.
Yeah, I can take it if it's so. We're already in the question mood. Then maybe let's read it out loud for those that cannot see it.
How does one determine which early exit to use? Is it heuristically set based on, for example, on the confidence of the respective early exits, or is it rather an anytime computation perspective, whereby computation may terminate abruptly and require a model prediction at any point in time?
So in this case, the early exits above certain threshold of the confidence. So you can basically say that, for instance, 90% accuracy or 90% confidence, actually not accuracy, is enough for you. And then you cut off the computation. Here you have to go to the last IC to do so, but you still are dropping the last element of softmax at the end. But this is based on the confidence threshold that you set.
Mm-hmm. So these are the confidence as defined by the softmax outputs.
Exactly. Mm-hmm. All right. I guess if there are any other questions related to this, I will also, be happy to take them afterwards. But yeah, feel free to interrupt me. It's just that I because it's full screen, I don't see the chat that well, but feel free to just raise your voice and I'll definitely answer the questions.
Okay, great.
Awesome. All right, cool. So we have the conditional computations pillar. We have a partial evidence pillar of zero-waste machine learning. So now let's move on to the last one, which is knowledge accumulation. And this type of research is actually widely known as continual learning, but it's not obvious that it's connected to efficiency. That's why I wanted to bring up the quote from Oriol Vinyals in his last talk or last chat with Lex Friedman, where he says, in other contexts, I guess, from protein folding, since he's in DeepMind and this AlphaFold was out, he said that some of these findings, in this case, model weights, will apply to the next iterations of training. But it's true that so far the weights you generally throw away, which feels very sad. So, well, Oriol is sad. I would say that it's more than just he said this that motivates me to work on that. But in principle, we do not use the weights of models that are already trained, and that's very often a cost of millions or hundreds of thousands of dollars. Not to mention the carbon footprint or the energetic effort that had to be invested in training a model, especially the large models that we have right now with billions of parameters. So now with this, the natural way of looking at efficiency of those models is through the perspective of continual learning, where you treat data that is coming in as a stream and not as a fixed distribution. Like you say, let's say you have the data set X1, the point of your network is to give the outputs Y1. Now, in the next time step, you get another set of samples, and the network remains the same, but you want to get other outputs. You want to get outputs yn, and potentially those outputs are different classes. Potentially you haven't seen the X2 before, or any classes or any instantations of classes in X2 and X1. And so this time axis, this time perspective of learning makes it either continual or lifelong learning, or sometimes people call it incremental learning. But the working principle is that you want to find a mapping between the input X data and output Y labels, and you want to do it within one function, f of theta. Now, what prevents us from actually seeing this to be implemented in reality, where people, if the data set changes, would usually just retrain everything from scratch, is the phenomenon called catastrophic forgetting. It occurs, or it's most well observed in the case where you have first on the left a data set, an MNIST data set of all the digits, and then in your training curve or training accuracy, you would see that it goes up to more or less 1 or up to almost 1, and then saturate. While if you split this data set into consecutive batches of data, or tasks, as sometimes people call them here in continual learning, you would get 0, 1 in the first one, 2, 3 in the second one, 4, 5 in the third one, and so on. And you train the model first on the task number 1. Once you move to task number 2 and you start training it there, the accuracy of your model on the previous task drops significantly. It actually catastrophically forgets the knowledge, the skills that it's acquired before. The one to be blamed for that is gradient descent. So that's the way we train contemporary neural network models. And it's actually quite intuitive that you don't get to the same results when you move from task 1 to task 2. In the task 1, let's say that you start with some point in this random space, and you end up with a minimum of task 1 local minimum of the loss function for your data set. Now, when you move from task 1 to task 2, because you observe new data, then you move away from this optimal point of your loss landscape, your loss manifold. And the way that we usually solve it in regular life is just by combining task 1 and task 2, and then averaging this, and trying to find the best of both worlds. And that's why stochastic optimization works, because you find something in between. You find something that is both okay for task 1, task 2 as well, and then you stay there. Now, people try to solve this problem of going with catastrophic forgetting, basically forgetting all the information from previous tasks, with multiple ways, either by regularizing your model so that it does not move too far from task 1 and from the optimal point of task 1, or architectural modifications, like by adding more heads to your network and freezing the previous elements of your network, or just by combining the modules of the network or subcomponents of the network. Now, for me, the most interesting, and it seems to be, I guess, one of the top trends in continual learning, is to use some form of memory. And so either rehearsing or replaying the past data samples while training your model on the current task seems to be working quite well. And obviously there are some hybrid approaches in between, but my talk, and actually the research that we're doing and continual learning and knowledge accumulation, is mostly focused around this rehearsal and replay methods. So obviously, if you rehearse past samples, you need to store them somewhere. And usually you use a buffer. The problem with the buffer is that it tends to grow as you accumulate more and more samples to be remembered and to be rehearsed in the next iterations. So there is a limitation, an intrinsic limitation on the memory consumption that you're hitting with this approach. The way that people try to solve it is by using generative modeling. So either variational autoencoders or generative adversarial network scans. And my line of thought, and actually some of our papers, follows this path. In fact, we have a even stronger hypothesis about continual learning, that generative models are in general more robust to catastrophic forgetting. And we show that's true in our paper last year, because their goal is to represent the data and not to discriminate between instances. So for discriminative models, what you have is, a network tries to find a representation of your data so that it can split dogs from cats. And, in the second iteration, in the second task, let's say you want to split planes and cars. Obviously, the representation learned for the first task is not going to be useful in the second. There are differences between cars and planes that are not included in the analysis of the data when you're training them on cats and dogs. However, the generative models have a very different objective. The way that they create the representation, their internal representation of a model, is to be more robust towards generating images and towards generating data. That's why intrinsically they don't have this limitation of splitting your data into separate space regions.
Just a question. Yeah. So regarding the generative models, I mean, it would be easy to reason, at least, that intuitively the generative models will also eventually suffer from catastrophic forgetting. I mean, if you stop showing it dogs, then it will eventually learn that the dog will never exist in the representation, right?
Yeah, that's absolutely true. It's not that they are avoiding catastrophic forgetting. The claim here is that they're more robust, which means that it's not so obvious to show that they forget instantly after showing the next class, because the internal representation has a different objective. But it's absolutely true. Like they do suffer from some form of distortion after a certain amount of time. In this case, actually, and that's very good leeway towards this slide, they have a different problem, which is the overlap in the latent space. So that's one of the, it's not exactly catastrophic forgetting that you observe, but it's the result is that the reconstructions of your data from the past starts to be of lower quality. So if you keep on accumulating the knowledge or keep on accumulating the information about samples coming in, and that's in the case of variation autoencoders, you do it in your latent space, then those latent space Gaussians that are used to model the representations start to overlap. And instead of getting, a sharp car or sharp horse, you start getting something in between, like a horse car or something around that.
All right, thank you.
And that's pretty much the same with the classes of zeros and ones. Like, previous data start to degrade, so the generations start to degrade, and that's a bit problematic when you want to repeat or rehearse your data from the past. So that brings us to our HK paper this year when we introduced multiband variation autoencoder. The question that we asked was, how can we align the data from the consecutive tasks that we observe in our data input in the latent space? So we posed the knowledge accumulation task as latent space partitioning. And we do it in 3 steps in multiband. First, we we train a encoder-decoder architecture to represent new data. Then we introduce the crucial element of this, which is a translator. So a translator takes the latent space and translate it into aligned latent space of both previous and current data representations. And then we do the global model retraining with the global decoder. So these are the 3 steps that we follow in multiband variation autoencoder. And additional mechanism introduces controlled forgetting when a previous task samples encoded in this common latent space that are close to each other. Our goal is, when training the decoder, is not to reconstruct the previous generation. As you see, it gets distorted so that the quality of this distortion influences the quality of the future ones, and it just keeps on accumulating the reconstruction error. But we substitute the objective with the new example. So instead of reconstructing the previous generation, we reconstruct new sample because of the proximity in the latent space combined or calculated as cosine between those 2 representations. And that allows us to forget. We have a parameter of controlled forgetting, and then we are able to accumulate and build these representations more robustly along with the time. And the example of the results that we obtain with this can be seen on this slide. So in the baseline model, you have MNIST data set, you split it into 1s, 0s, and so on. In task 1, you have just classes 1, so it's easy. Then you add the task number 2 when you have zeros in your batch. And as you see, the data starts to, from the previous tasks, starts to degrade. You start to see, the overlap in your latent space between zeros and 1s. And then in task number 3, when you introduce classes, objects, or data samples of classes 1 and 2, you should observe 1s that are close to 1s from the task number 1. I mean, ideally, the model should know that if it already has seen the 1s and then put the 1s in the space close to the ones it saw before. That's not the case. Also, the data keeps on degrading and you start to see blurs all over the place. So in our case, what we propose is this idea of latent space separation and latent space knowledge accumulation. And that can be visualized in the bottom. You see that the separation between the classes are instant, and therefore the degradation is much smaller. And finally, when we add ones and twos, the ones are accumulated around the same as part of the space, and they do not spit over or get over to other classes. So they do not disturb other class representations, and therefore the quality of reconstruction is much higher. We actually compared that with other methods, with competitive approaches, and we looked at the Freshlet metric for the reconstruction, also precision of reconstruction, recall of reconstruction, and this seems to be working quite well. But what made us even more interested in this method, and actually what we are quite happy about, is that not only it does not forget the previous samples, so it does not degenerate that much on the past samples, but it also shows some proof of forward transfer, which is the capability of a model to actually improve future results based on the past iterations. This is visualized here in the right side, of the slide, where you have the number of tasks. So you have 0, 1, 2, 3, 4, and the tasks finished. So we go with time from 0 to 4. And then this is the baseline model, and this is our multiband variation autoencoder. So the beginning of each row means that we are getting lower results, and this is Wasserstein distance metric, so it should go as low as possible. And you see that for each of the new tasks that we're observing, we're getting better results than our competitive approach. So we are able to leverage the previous tasks, so knowledge accumulated in the previous tasks, to improve the results on the task that is currently at hand. And that is it from the zero-waste machine learning perspective I have so far. We are continuing work on this within a group at Ideas NCBR. So if any of the conditional computations, partial evidence, or knowledge accumulation topics are of your interest, I'm happy to discuss collaboration opportunities, or internships, or meetings, etc. Now, that's not obviously only my work. It's been a great honor to work with all the collaborators, and also I acknowledge the support of multiple funding agencies to make this work available to everyone. And so, yeah, that's pretty much it from the zero-waste machine learning merit perspective. Just in case you're interested in thinking about some future steps in your career, there's the computer vision group that I'm just started to build, and we have just initiated the Ideas NCBR AI Center in Poland with some 10 million euro per year funding and up to 200 researchers to be recruited. One of the groups is computer vision group that I'm leading, and we have quite interesting offer for PhDs, postdocs, and team leaders. And last, maybe marketing ad, we are also organizing the machine learning summer school next year. This year it was a great privilege, and one of the reasons why I'm actually here, because we met with Envin to meet with people from all over the world. We had people from Montreal, from Mila, we had Razvan from DeepMind, we had folks from Oxford, Cambridge, Andrea from Vancouver, UBC, and so on. So there was quite a bit of international crowd in Krakow this year, and next year we'll also going to be organizing this. So with this, I think I'm done, and I'm open for questions or comments or anything else. Thank you so much.
Thank you, Tomasz. Do we have some questions?
I have a question about the first part of the talk, if that's all right.
Sure.
Yeah, I was just curious, Tomasz. So you've presented these two ways of forming the classifier. So either you would make the predictions at the intermediate layers, or which would be like ensemble-like classifier, or alternatively, you would concatenate, as far as I understood, the representations from these intermediate layers. So are there trade-offs between these two approaches? Or is one obviously better than the other?
Do you mean the two components here?
Or yeah. Or maybe I got confused probably then. So it's actually different. It's actually this parts of the same solution. So they're not like different.
Yes, it's a part of the same solution. It just allows you to basically make use of two mechanisms. One it's the cascading link between the ICs, and the other is ensembling predictions. So these are, I would say, like two parts of the same solution. These are not one or the other. But in this case, yeah, we are using both the predictions as well as the links between them to propagate them. So that would be the contribution that we proposed.
Okay, got it. Sorry for the confusion from my side.
No problem. Maybe I was not clear enough as well. I need to fix this next time I talk about that. Thank you.
Hi, I also have a question related to the first part. It was I who asked about this, whether you used the confidence for the early exiting. And you mentioned that is very typical to use a confidence level. And a follow-up question then is, I mean, I guess it's oftentimes it could be that things are inherently unconfident, or like there's uncertainty in the data of some sort. And then I would assume that going for the most confident prediction is not necessarily the best thing. So do you have any comment on that?
Oh yeah, I mean, definitely the confidence is not the best. It doesn't guarantee you the result. Like, you know, some data samples can be classified confidently with the wrong label, and that's where the errors come from. That's where the ensembling helps quite a bit. Because you are quite unlucky if all the internal classifiers incorrectly classify with a certain confidence the same sample. I guess that's one of the reasons why we are actually getting better results than the baseline model in this case. Because of the ensembling, you just get additional, you know, information, and if you properly propagate this and combine the results, you are able to outperform it. But I 100% I agree that confidence, I would say, is a proxy, which does not guarantee you the result. It's correct.
Yeah, thanks. And now that you have this slide, I was thinking about you know, efficiency, how you measure that, and so on. I guess it would depend also quite oftentimes on what architecture that you have. Do you have any thoughts on this, and how would you report that typically? Do you just select, we use this GPU and this is what we get, or?
Yeah, so that's an excellent question. We just finished a Google workshop on efficiency in terms of sparse neural networks and adaptive computation. And Dave Palmerson from Berkeley yesterday had the same line of thought, like, how do you actually compare the efficiency? So we use flops. This is like number of floating operations. It's technically the most clear and kosher way of measuring the efficiency of algorithms. However, it highly depends on the architecture. So number does not depend, but the energy consumption, the time that it takes to compute a flop is definitely dependent on the architecture. So in that case, what he advocated, and I kind of lean towards this line of arguments, is that time, assuming a certain architecture, is still the best proxy for performance. Now, there is another one, which he also mentioned, and I think it's a bit problematic for us researchers to measure that, but memory accesses. So number of times you access memory, which is also very costly, is another idea for measuring efficiency. I would say that, you know, ideally, if you have all the time in the world, you probably should compare all of them and report all of them, and then, you know, your paper will be complete. But practically, that's very tough. And practically, probably the easiest way is to choose one of those and just keep on arguing that this is the one that describes your problem the best. For me, it's flops, as it's the one that I can compute quite easily. Time is also okay. Now memory access is just, from an implementation point of view, much trickier.
Thank you.
Tomasz, if no one else has a question, I wonder about the third part of the talk. So it's not like, so my question is not that well thought, because I'm not like an expert in the continual learning. I was recently reading a paper, I think it was from a group at La Sapienza in Italy. And what they were proposing, like their sort of take on trying to address the forgetting aspect of when doing multitasking, was using centroids. I'm not sure if you were comparing it. Do you have any thoughts on that? Like centroids are prototypes. I think I think it's called prototype neural networks. I think it comes from Toronto. I forgot exactly. Probably Rich Zemel was one of the supervisors of that project.
Yeah, the prototypes, that's the way that is quite close to the work that we are currently looking into. It's either prototype or prototypical neural networks. There are some discussions on like feature replay or centroid replay in the past. It's a very vivid area of research, I must say. In Montreal or Toronto, DeepMind, there's CVC in Barcelona that works pretty intensively on that. We don't compare with all of them. I think here what the comparison was mostly given with respect to, so EWC, generative replay. EWC is the regularization method. Generative replay, it's the baseline for the generative models to be replayed, and then some variation autoencoder and GAN-based models. So it's not exhaustive for sure. We focus mostly on the rehearsal from generative models, and we try to convince in the paper, and I encourage you to take a look at it. We try to convince the readers that that this generative approach is the most robust and the most interesting. But it's the centroid or prototypical approach is also quite interesting. Exemplar-based continual learning, that's something we look into as well. So it's not about centroid, finding centroids of your representation of your class, but selecting the exemplars out of them and then looking at which exemplars provide you with the lowest amount of catastrophic forgetting. There is one good survey out of CBC in Barcelona coming out in PAMI. It's a fairly long-standing paper. I think it's from 1 year ago, but it gives you a full-blown overview of all the method and compares it quite widely. So I would, if you ask me what's the best method for continual learning right now, I would probably point you to that paper. But yeah, I mean, this again is super active area of research. Like at this NeurIPS, we're coming to New Orleans. So if any one of you is actually there, like, just give me a shout and we'll definitely catch up. But there are at least 40 papers on the topic, so that seems to be relevant and I'm not sure in mainstream, but at least it's observed in research in the main area.
And each paper is probably claiming to be the state of the art at the time when the paper was written, right?
That's exactly true. Like HCAI paper was published 4 months ago or 5 months ago, and it was submitted in, I think, January or December. So, it's machine learning. So you wake up and there's 50 more papers on the topic you're working, and you have to sort of live with this.
Yeah, thanks a lot for the perspective. That was very useful.
Thank you so much.
Great. Are there some final questions? Otherwise, thank you very much, Tomasz, for this talk. The next seminar is next week, October 20th. Hedvig Källström from Royal Institute of Technology, KTH, in Stockholm, will speak about compositional, structured, and interpretable models. So welcome back in 1 week. And thank you again for today.
Thank you. Have a good day, guys. Take care.
You too. Bye-bye.
Thank you.
Thanks.